Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Houston, we don't have a problem. And today we're going to talk about actually what something is very difficult to understand. The concept of energy. Now I know you understand the concept of energy in some sort of a sense, like you have so many calories in your food, or you just understand that something takes more energy than the next. These are the forms of energy right here. We've got energy equals, there's an energy called a K, a UG, a US, ETH, E chemical, and there are other ones, but the main ones we're going to look at are these in this class. So the first one, we talk about kinetic energy. That is the energy of motion. So when something is moving, it has kinetic energy. You've probably heard the term, somebody, well, you haven't, but the idea that someone is kinesthetically gifted. You could say that LeBron James or Michael Jordan were very gifted in the art of moving. So we have a ball hitting a building, the building's getting crushed because the ball is moving, so that's got a lot of kinetic energy. And that's the K in that equation. The second one is gravitational. When you have something that's up high, and it's of course going to come down on the earth, that is called gravitational. And it's got a U on there later on why we have U's and whatnot. And then the next one we're going to call is the US, and that's the spring energy, right? So when the young man is pulling back, he's created a spring. The bow is the spring, and the arrow, of course, is going to be launched. Another one you're familiar with is thermal energy. So this is heat. Now this is a weird one because, well, we'll talk later about why it's weird. But this is, by the way, the Blue Lagoon in Iceland. I got a chance to visit this. It's this huge hot springs, a lot of thermal energy. And the one when you think about energy probably oftentimes is you think about this one, chemical energy. So when you eat something, it has so many calories in it. So the monkey's eating something. By the way, the energy is stored in the chemical bonds. So if you go back to your recollections from your chemistry class, there's covalent bonds and ionic bonds, all those kinds of things. And when you break those bonds, it releases energy, usually in the form of heat, thermal energy, into the body, which then can allow you to move your body to think and do the things that you do on a regular basis. And the last one we won't go into great detail is, and not used at all in this course, but it's interesting to note, is that kind of the basis of a lot of energy is nuclear energy. So every star, like our sun right here, has nuclear energy in it, and it's being transformed actually from the nucleus of the atom. So if you have the nucleus, what it does is the nucleus weighs, so this is a nuclear reaction, a neutron hits a uranium-235 atom, this is nuclear fission, and then what happens is it then turns into a uranium-236, it's very, very, very unstable, and then when it splits, it actually loses a tad bit of mass, and that lost mass is converted into energy. This is actually Einstein's famous E equals mc squared. So we've got these different kinds of energy, or forms of energy, we say. We've got kinetic, we've got gravitational, we've got spring energy, we've got chemical energy, we've got thermal energy, we've got nuclear energy. And what we can only do energetically is we can only do what are called energy transformations. I can't like create new energy. The amount of energy in the universe is the amount of energy in the universe. You can't change it. You can't create or destroy energy. Let's jump to a quick little demonstration about different energy. First up, let's look at Newton's cradle here. As this ball moves, all right, so I have a particular kind of energy, gravitational potential energy, and it then converts to kinetic energy, and it hits this one, it knocks them all over there, and it converts this to gravitational kinetic energy. Conversely, I can pull back two of them. Watch what happens. And we have our spring device here we have. So right now, there's just gravitational potential energy, but then as it falls, it's converted into kinetic energy, and then as it goes up, it's kinetic spring energy, and then the process repeats itself. And lastly, we have the ball. And a lot of people don't understand how balls work. So if I have a ball and I drop it, right? When I drop it, it bounces. But actually what's happening is as the ball hits the ground, it compresses the ball, and then the ball creates a spring energy. So we have potential to kinetic to spring to kinetic to potential and back and forth. An often looked transformation that we miss is what's happening here. I've got a weight and I drop it onto the table, but it doesn't bounce, right? It's not bouncing. And if I keep doing this, what I'm going to do is I'm going to go like here, I'm going to read the temperature. I can read the temperature of this, and if I keep dropping it, it is doing a little bit of bouncing, but most of the energy is going into thermal. And if I keep doing this a few more times, it's going to get hotter. So the temperature sensor just showed that this increased by 0.5 degrees Celsius by me just dropping it over and over again. And if I keep dropping it over and over again, then it's going to be converted to thermal energy. We have a base runner. Let's think about what's going on. So the base runner has kinetic energy as he's sliding into second base. And what kind of energy is it converted into? It's converted into thermal energy. So that he's going to have friction between him and the ground, and it's going to be converted to thermal energy. Or what about this? At a campfire. So you have the cool campfire, and if you're at the campfire, this is chemical energy. The chemical energy in the bonds in the wood is being converted into thermal energy. A bit more of a complex one is a springboard diver, like Olympics or whatever, right? So as the diver hits the springboard, he has spring energy, right? Makes sense. Spring energy, but then he's going to rise into the air, so that means he's moving, that's going to be kinetic energy. But then he's going to reach a top, and at that top he's going to have gravitational energy, and then he's going to fall back to kinetic energy. So this is kind of a complex problem. It starts with spring, it goes to kinetic, gravitational, kinetic. So it's a longer process. So we could talk about a million different examples of energy. I mean, even as I have lunch here in a little bit, I'm going to take chemical energy and it's going to convert into thermal energy. That thermal energy is going to move and be converted into kinetic energy as I move my body. And when we talk about energy, we have to actually define two things. We've got what we call the system and the surroundings. So let's talk about the system. So the system is the subset of the universe that's being studied in a particular problem, right? And the surroundings is the rest of the universe. The surroundings. And we have, as it turns out, two kinds of systems. Actually, there's a third, but we're not going to focus on the third type. So that we either have an open or a closed system. In an open system, it allows for transfer of energy and matter to the surroundings. Okay? And then the closed is the same thing, except it does not, basically, no matter transfer. So it allows for transfer of energy and to the surroundings. No matter. I take this word out here. And that is what a closed system does. So let's give a couple of examples. A runner running. That's an open system because not only is he transferring energy to the surroundings, right? He is running very hard, and as he runs, he is also sweating. And as he sweats, then matter, the moisture, is evaporating off him. So he gets lighter as he runs. So matter is being transferred to the air as he runs, as is heat, because the energy from his body is going out and warming up the air. Another good example would just be some boiling water would be a good example of a open system, because as you boil water, though, if you let it boil for a long time, of course the water will all, or soup, I think this is a soup, it's going to boil all away. That means it's not going to fill the room. That's why when you walk in and your mom or your dad are cooking or baking or something, you're baking cookies, the reality is that smell that you smell is it's an open system because the chemicals in the chocolate chip cookies or whatever they're making or the soup are filling the house, which is kind of cool, right? A closed system, my good example would be a hair straightener. So if you straighten your hair, the energy that's coming, so electrical energy, we can talk about that. Electrical energy is going into the hair straightener, converted to heat energy, but the hair straightener isn't getting heavier. It's not getting lighter. There's no loss of mass when you do the hair straightener. Another example would be just like a watch, an Apple Watch or whatever, is the chemical energy stored in the batteries is causing everything, it's creating thermal energy, but the watch doesn't get heavier or lighter. So a good way to look at this is with this diagram here, is we've got a system and all the energy process, converting from kinetic to U is what we call potential energy, we'll get to that in a bit, to thermal energy, to all these kinds of things, are staying within the system. But in an open system, and this is actually going to be a really important point, in an open system, that energy can flow out of the system as either heat or work. And work is an important concept. In fact, that is the big topic of our next video. And so if it's transferred out of the system, it can cause something to do what physicists call work, which is a very specific definition. Don't think of work as, you know, I go to a job or whatever. We'll define it in the next video. Anyways, Houston, we don't have a problem. That's a quick introduction to the concept of energy, and I haven't even defined it yet. I'll do that in the next video. We don't have a problem.